Can somebody remind me what is a transfer function? Okay, suppose I have a block. This block is represents the relationship between an input and an output. This block is a transfer function in the frequency domain, and it's the ratio of the output in the frequency domain after the Laplace transform over the input in the frequency domain after the Laplace transform. So we capture the input-output relationship through the transfer function, and it is widely used in linear control systems, like the one we have in this course. So it is defined as the ratio of the Laplace transform of the output over the Laplace transform of the input. So when I have these blocks, they represent an input-output relationship. So as an example, so this is a time domain example, but the reason we can do this in time domain because this is a static circuit. It doesn't have a time element. But once you have a time element, then we run into issues because we have dynamics in the system. So we cannot have a transfer function representing the system unless we're referring to the frequency domain version of the problem. So if the output voltage is equal to R1 over R1 plus R2 multiplied by the input voltage, then this is the transfer function of the system, which captures the input-output relationship. So static systems, such as the voltage divider, are represented by a block diagram with a constant gain. Linear time invariant dynamic systems, like the ones we use in this course. By linear, we mean that we have superposition. For example, if I have two inputs, the outputs will be. So I can use the superposition principle, and if I scale the input by some number, then the output will be appropriately scaled by that same number. When I say time invariant, it means that so it doesn't mean that it does not depend on time because it's a dynamical system. Any dynamical system depends on time. It just means that the dynamics, the relationships, the mathematical representations of the system do not change. For example, if I have a differential equation describing the input-output relationship, this differential equation tomorrow is the same differential equation. It's not going to be affected. So that's what we mean by time invariant system. The parameters, the constants of the system do not vary with time. For example, the mass is just a fixed number. You don't have mass as a function of time. These things do not vary with time. So it's a time invariant system. And we represent them by transfer functions, where we have the input multiplied by transfer function being an output, or the transfer function being the output over the input in the frequency domain. So if I have an input x of s, so the input is x of t in the time domain. After the transform, it's a capital X of s. Similarly, the output is y of s, which is equal to g of s over multiplied by x of s. What is g of s? It's the Laplace of the output over the Laplace of the input. So what are the properties? So the properties is defined for linear time invariant systems only, which is these are the kind of systems we use in this course. Transfer function is the Laplace transform of the impulse response. So we talked about the impulse function because its Laplace transform is 1. So if I have a system, I can give it a test signal, impulse signal, and look at the output and take and it's the Laplace transform of that output. It's the same as it's the impulse response. When I say response here, I mean I give a system a certain input and I see the output. So if I say impulse response, it means that the output due to an impulse input. If I say step response, it means the output due to a step test signal. And all conditions are assumed to be 0. The calculations of the transfer functions, meaning the initial conditions are 0. For example, x of 0, x dot of 0, all of these derivatives at 0. And the initial point, at the equilibrium point, are actually 0. The transfer function is not a function of time. Yeah, so let me just edit this real quick. Yeah, it is not a function of time. It's a function in the frequency domain. So we're working in the frequency domain here. So let's take an example. If I have a step input here, U, I have an output 3 minus 2e to the power of minus 3t. What is the transfer function of the system? Can you guys help me compute it? G of s, what is G of s here? G of s is equal to what? Can somebody help me?
output over
Output over input or Laplace transform of the output over Laplace transform of the input?
and Laplace.
Okay. So we have the Laplace transform of the output, y of t. Then we have the Laplace transform of the input, u of t. So what is the Laplace transform of y of t? What is the Laplace transform of 3? Yes, Faisal.
It's 3 over s minus 2 over s plus 3.
3 over s minus 2. Yes, you're right. 3 over s minus 2. So this is a step, right? Multiplied by 3, so it's just 3 over s minus 2. And this is just an exponential, so it's a shift in the frequency domain. It's s plus 3 over 1 over s, right? Which is simply 3 minus 2s over s plus 3. This is the transfer function of the system. If I multiply this by 1 over s, I get y of s, which is the output of the system. Okay. So how do we get a transfer function from an ODE model, from an ordinary differential equation model? So we have two variables, the input and the output in the differential equation. The procedure is as follows. You apply the Laplace transform to the differential equation. You assume zero initial conditions. Solve for the ratio of the Laplace transforms of the output and the input. And this is how we get the transfer function of the ODE. From that transfer function, we can do a lot of things. That's why we care about transfer functions. Again, transfer functions are only defined for linear time invariant systems. Can you guys get me the transfer function for this differential equation? I'll give you 3 minutes to get it. I'll set a timer right now for 3 minutes. If you have any issues or difficulties, let me know. Otherwise, I'll assume that you're working on it. Is there an exam today for an ICE course?
It's tomorrow,
Which course?
3:15.
Well, what is the title of the course? Because I see the number of people who are absent is larger than usual.
It's engineering statistics.
Is it difficult?
I find it kind of average in terms of difficulty.
Okay. There is no, okay, so all initial conditions are assumed to be 0. So my timer is up. Have you guys got it? Yes, Fauzi.
It's square
Okay, S square,
plus 3s
3s,
plus 4 over 2.
Okay, what is the output of the system?
Output x of s
Okay. What is the input of the system?
y of s.
Is this x of s over y of s?
Yes.
Okay, I think you're right. I mean, if we assume that the output is x, you're right. But I think here the output is y. So we have the reciprocal of this one. Okay. So if we assume that the input is x, I think your calculations are right. But maybe because I did not clarify which is the input, which is the output, there was a little confusion. So let's say that this is the input, and y is the output. Okay. So how do we get the differential equation, the Laplace transform of this ODE? It's very straightforward. We have double derivative here, so we have s square y plus 3sy, because we have one derivative, plus 4y. This is equal to 2x, right? So take y as a common factor. We have s squared plus 3s plus 4 is equal to 2x, right? Which implies that y over x is just 2 over s squared plus 3s plus 4. Usually we have systems in which the denominator is of a higher order than the numerator. And there are many reasons for that. But you can think of it as realistic simples will have that, realistic models will have this kind of phenomenon. All right? Yes, Mazen.
Yes, doctor. And when we solve this kind of problem, you said we assume that the initial conditions are 0. What do we mean by the initial condition is 0?
Okay, so we have derivatives here, right? If I look at the Laplace transform of the derivative, we need to use the initial conditions of that function y of t. Let me just pull up the expression for the Laplace transform so we can clarify what I mean. Let me see if I can find it. Where- Yeah. So, for example, Laplace transform of the second derivative of f is s squared capital F of s minus s f of 0 minus f prime of 0. These are all the initial conditions of the system, and it is 0. This is what we mean. Okay? Because you have a differential equation, you're solving it with respect to an initial condition. So we assume 0 initial conditions for the system. The computations of the transfer function. Clear?
Yes, clear.
Yes, Fauzi.
How can I know what is the input and what is the output?
So usually the input is the one on the right in our notation in this course. And the output is something that varies with time and it has exponents.
Okay.
It has like multiple derivatives, I mean.
Okay.
If there is a question which does not clarify what is the input or what is the output, you can ask me and I'll let you know. Because you need that information. So there is what's called the zero state response. It's the response of the system to a given input with all initial conditions equal to 0. Yeah, it's what we're working on actually. So now let's go to the next topic, which is the inverse Laplace transform. So we have a definition similar to the Laplace transform, the inverse. And then we will use partial fraction expansion to do inverse Laplace transform. So what we do is the following. We represent the system as a function of we represent the system as a transfer function, capturing the input-output relationship. And we use the inverse Laplace transform to figure out what is the behavior of that system. And then once we do partial fraction expansion, we'll have three kinds of poles. I will discuss what a pole is, and we will have some examples. The inverse Laplace transform will be one last topic before the final topic of this unit. And then we will talk about what's called the initial and final value theorems, which are quick theorems that we can cover quickly. So similar to the Laplace transform, we have an inverse Laplace transform. So for the Laplace transform, we're integrating with respect to t, f of t multiplied by e to the power of minus s of t. For the inverse Laplace transform, we have a similar definition, but you are actually integrating with respect to s. So s is a frequency. S is equal to sigma, the real part, plus some j omega. So we're going from minus infinity to infinity for the omega. So we're integrating with respect to all frequencies. And we have f of s e to the power of st. We have 1 over 2j pi. So this is a real number that is greater than the real part of all singularities of f of s. So we will not use the definition in order to compute the inverse Laplace transform. But this is to state that there is a definition that you can use on the inverse Laplace transform. So we will focus in this course on the case in which f of s is a rational function. So it's a fraction. So we have two kinds we have two kinds that we care about. So f is a rational function, meaning that it's equal to some polynomial n of s over some polynomial d of s. F is called proper if the degree of n is less than or equal the degree of d. It is further strictly proper if the degree of n is strictly less than the degree of d. So if it is strictly proper, it implies that it is proper, but we cannot do the opposite. For example, here we have degree 2 over degree 3, so it is proper. But if this is 2 over 2, it is not strictly proper. So this is a stronger property, the strictly proper function. So is this one proper or proper, strictly proper? What kind is it? The first one. Somebody tell me. Yes, Fauzi.
Strictly proper?
What about the second one?
Just proper.
Yeah, similarly, the third one is strictly proper, and the fourth one is proper. And why? We look into the degrees of the numerator and the denominator. So for strictly proper, so degree of denominator is greater than the numerator, and similarly for the others. If it's okay, suppose I have s cube here, and here s, then this is called improper. And the reason we don't care about improper functions in this course, because these will have divergence and the system will blow up. Because if you take the inverse Laplace transform, these kind of functions, you will find that they are not realistic. So for whatever input you will have, the system might explode. So these are not stable systems, so we don't care about them. I mean, still, you might have a strictly proper system that is unstable, and we will see these kind of systems. But the thing is, these unstable systems can be stabilized through an appropriate choice of a control parameter or some appropriate control selection. So there is some hope to fix these kind of systems that are proper or strictly proper. Okay. Also, the other thing is, even if the system is improper, sometimes we can still work on it by long division. And we can have, let's say, a strictly proper version of it. But for partial fraction expansion, the way we do it here, we work with proper rational functions. So again, we have a rational function represented as n of s over d of s, where these are polynomials. The roots of n are called the zeros of f, or the zeros of the system, and the poles of f are the roots of d. So the poles, the location of the poles is very important in control because it tells us a lot about the system properties, and we will see that as we progress in the course. So if we have an example, g of s being s plus 1 multiplied by s minus 2, then the zeros of g are minus 1 and 2, because these are the roots of the numerator. And the poles of g are 0, minus 3, and minus 4, because these are the roots of the denominator. Similarly, we have these examples. So we have 1, 0 at minus 2 for the first example, and two poles, minus 3 and minus 4. Here we have 1, 0 at 3 and 1 pole at minus 0.5. Here we have 1, 0 at minus 3 and 2 poles, 2 repeated poles at 0, 1 pole at minus 1, 1 pole at minus 2. Here we have 1, 0 at minus 3, 2 repeated poles at minus 1, and 2 poles at 2 plus minus 3j. So what we will do in this course, instead of trying to find the inverse Laplace transform of this rational function directly, which can get complicated, we will utilize partial fraction expansion to split this function into easier parts to find their inverse Laplace transform. So if I have 2 over s, then it's a unit step multiplied by 2. So the inverse Laplace, so it is an easy function to find its Laplace transform. This is just 2 u of t, right? Similarly, if I have 3 over s plus 3, then I know that I have a shift in the frequency domain, so I have e to the power of minus 3s, 3t. Then we have here 3 u of t multiplied by that, right? Similarly, for the third fraction, because we have easier fractions to work with, we can immediately find the time domain representation of these fractions. So that's why we want to utilize the partial fraction expansion so that we get simpler terms to deal with. And these terms are terms that we can easily find their corresponding time domain function. So how do we obtain these terms? Any ideas? Any idea? How do we do partial fraction expansion? You have done this in other courses. Okay, where did you see it last time? In which course? Okay, nobody remembers this?
Doctor, I don't remember يعني very well, but I think we should separate each element like for s and plus 3 and s plus 2, and I think we should add letters a and b and c, I think, and also solving for each one, something like this.
Good. So we have we have 3 poles here, roots of the denominator, s minus 3 minus 2. So we can have, as Mazen mentioned, we have some a over s. This comes from the first root. And then we have b over s plus 3. And we have c over s plus 2. And then we solve for a, b, c. So we will have a refresher over these ideas. And sometimes you have repeated poles, sometimes you have complex poles. So we have to also worry about how to address these. So we will take care of them in this course. Okay. So we have 3 cases: distinct poles, where the poles are not repeated or anything. We have repeated poles, and we have complex poles, and we will address them appropriately. Just give me 1 second, guys. I need to recharge my laptop. Okay, so if F is strictly proper and all of its poles are distinct, then F of S can be represented as follows. You have summation. Let's say we have n distinct poles of AI, some constants that we solve for over S minus Si, where Si is the pole. What is AI? You multiply F by S minus Si and then evaluate it at Si, the pole of the system. So the inverse Laplace transform is the following. It's the summation. For every term, what is the inverse Laplace transform of this guy? We have AI. It's a parameter, so it doesn't affect the analysis. And this is just a shifted step. So you have a step. That step is, so this is for t greater than or equal to 0. That step is just equal to 1 when t is greater than or equal to 0. We can multiply by u of t, and then we have e to the power of si t. That's pretty much it. Actually, there is something to notice here. If si is negative, okay, then this function will vanish and y will go to 0, the output of the system. If si is positive, then this system will blow up and y will go to infinity, the output of the system. And that's why we say that the system is stable if the poles are negative. And it's unstable if the poles are positive because of this reason. Because once you do the inverse Laplace transform, this exponential function is critical because it can either go to infinity or it can go to 0. If it goes to 0, then it's a stable system. We will discuss these ideas later, inshallah. I just wanted to give you a heads up on it. So let's look at this example. So we have f of s being equal to minus s over plus 5 over s plus 1 over, multiplied by s plus 4. So this is equal to a1, the first pole, over s plus 1 plus a2 over s plus 4. So what is a1? a1 is simply you multiply f of s by s plus 1. So we have s plus 1 multiplied by f of s. What is the pole here? It's minus 1, so you evaluate it at minus 1. What do we get? If I have minus 1 multiplied by minus 1, then it's just 6 over 3. This is 2. Similarly, what is a2? You multiply s plus 4 by f of s, and then you evaluate it at s being equal to minus 4, which is the pole of the system, which is the root of the denominator that we're looking into. So minus 4 minus 1, it's plus 4 plus 5, so this is 9. And then we have here minus 3, so we have minus 3. This implies the following. This implies that we have here minus 2, minus 3. This implies that the system, this function can be represented as 2 over s plus 1. Let me get a pen here, just 1 second. 2 over s plus 1 over plus minus 3 over s plus 4. I'll pause here for questions if something is not clear. Any questions? This is an important thing. You have a test on it next week. Yes, Faisal.
Doctor, the value of S, should we always take it negative or in opposite way?
So you look at the pole of the system. So if I have a denominator of S plus 1, then what makes that 0? It's minus 1, right? So it's naturally have that negated. Any other questions? All right, we'll move on. So there is an alternative way of obtaining AI, which is the following. Basically, you have A1 over S plus 1, and you have A2 over S plus 4. After the partial fraction, you take a common denominator, and then you have A1 is plus 4, A2 is plus 1. After that common denominator, then what happens is that after you take S as a common factor, you have A1 plus A2 multiplied by S, and then you have 4A1 plus A2 multiplied by S. So you know that A1 plus A2 from the original function are equal to what? Are equal to minus 1. And you know that 4A1 plus A2 are equal to 5. So you have a system of two equations with two unknowns, and once you solve it, you get A1 to be equal to 2, and you get A2 is equal to minus 3. This is an alternative way that you can do. I mean, it's just simple algebra, so I will not go through it in details, but you get the idea. So what is the inverse Laplace transform? After we get this, it's 2, which is A1, e to the power of minus t. Why? Because the pole here is at minus 1. Then you have minus 3, which is A2, e to the power of minus 4, because the pole here is at minus 4. And this is for t being greater than or equal to 0. Okay? Any questions? All right. The next case, so the distinct poles case was straightforward. Also, the repeated poles case is straightforward, but there is a small twist. Here we have this function, 5s plus 16. Do you guys want to solve an example for distinct poles before we move to repeated poles, or do you think it's clear? Because I can give you an example right now to do something. It's a small practice. We take a quick poll. Exercise. Please answer the quick poll. All right. Keep going. Please vote. Seems that majority want to do an exercise. Okay. So I'll give you a short exercise. So let me go back to the. All right. Let's work in this with this example. We do the following. Suppose instead of this function, I have the following function. We have f of s is equal to s plus 2 over s plus 3 s plus 5. Find the inverse Laplace transform of this function. Do the partial fraction expansion. This is equal to what? Yes, Fawzi.
Doctor, can you put the formula?
Sure. So AI is equal to S minus the pole corresponding to AI, f of s, evaluated at the pole. Any luck? You guys figured it out? Still trying? Yes, Abdullah.
Is A1 minus 0.5 and A2 1.5?
Okay, let's verify. So A1 is simply I multiply by s plus 3, so we have s plus 2 over s plus 5. This is evaluated at s is equal to minus 3. So we have minus 1 over 2. You're correct. What about A2? What was it?
1.5.
Yeah, so we evaluate minus 5. So we have minus 3. Then we have here minus 2. We have, yes, 3 over 2. Correct. So what is y of t in this case. What is the inverse? So what is the corresponding inverse Laplace transform? This is equal to what? This is equal to minus 0.5 over s plus 3. And we have plus 1.5 over s plus 5. Can somebody do the inverse Laplace transform for me? This function? Yes, Abdul Wahab.
Minus 0.5 e to power minus 3t
0.5 e to the power of minus 3t
plus 1.5 times e to power minus 5t.
and t is greater than or equal to 0. So here you either write t is equal to greater than or equal to 0, or you multiply everything by y of t. Okay, one of them needs to be there, either multiply by y of t, so meaning that everything is multiplied by a step, or you have to decide that t is greater than or equal to 0. This is important, okay? All right, any questions about this part? Okay. Keep going. So the next case we want to talk about is the repeated poles case. Sometimes you have two poles. So how do we address them? For example, I have s plus 2 repeated twice here. So what we do is the following. Because we have two repeated poles, we have a11 over s plus 2 squared, and then we have a12 over s plus 2. So because you have two poles, then you still need two corresponding fractions, but they are different. So the first one, you have the highest order, then the second one, you have the just to the power of 1. So if I have, let's say, one, like something here, call it n of s over s plus cube, over s plus 3 all cube, then I will still have a11 s plus 3 all cube. Then I will have a12 s plus 3 squared. Then blah blah blah. I will have a13 over s plus 3. So you will still have as many terms as the number of poles, even if they are repeated. However, the computations of the coefficients, the computations of the constants will be different. For example, here for a11, you treat it normally because you multiply by s plus 2 squared, multiplied by f, so evaluate minus 2, you get some number. Then for the second term, because I cannot multiply this by s plus 2 and evaluate it minus 2, because if I multiply this by s plus 2 and then evaluate it at minus 2, this part will cancel this part, but then I will still divide over 0 and we will get infinity. So we want to avoid that. So the remedy here is as follows, is to take the derivative of the entire thing. You take the derivative of this guy. So once you take the derivative of this guy, and then evaluate at s minus 2, you will have a certain coefficient 1, like certain number. And for the third pole, which corresponds to minus 5, business as usual works. Okay? So let's go through it step by step. So we have two poles, a11 over s plus 2 squared plus a12 over s plus 2 plus a2 over s plus 5. Multiply by s plus 2 squared, f squared by s plus 2 squared, f of s by s plus 2 squared, and evaluate minus 2, you get here minus 10 plus 6, and you get here over 3, so you will end up with 2. Now we take the derivative of this guy after you multiply by s plus 2 squared. So what is the derivative here? The derivative is simply take the denominator, square it, s plus 5 squared. Then you have the derivative of the numerator multiplied by s plus 5 minus the denominator, which is 1, multiplied by the numerator. So you get 5s plus 16. So everything here is the derivative. Then you evaluate at s equal to minus 2. So you will have here 3 squared, which is 9. And here you will still have 9 because you'll have 5 multiplied by 3, 15, minus, you have 5 by 3, again 15, plus 16, which is 1. Wait, we gotta stop here. So you have here 50, so here, so yeah, so you have plus minus 6. You will end up with 1. Now for A2, it's business as usual. You multiply by s plus 5. You have 5s plus 16 over s plus 2 squared. So similarly, you get minus 1. Because you have minus 9 over, you will have minus 8 over, minus 6 over 6. Yes, Muhammad.
دكتور ما فهمت حقت A1 اللي آخر شيء سويته.
Okay, the after with the derivative. Which one? So there was A1.
اللي سويته
A11 or A12?
لا مو A11 دقيقة.
A12.
لا A11 أجل.
A11 is simply you multiply by s plus 2 squared, and then you evaluate at minus 2. The very first one, right?
Yes.
A12, you take the derivative, and then you evaluate at s minus 2. Then A2 is business as usual. So you multiply by s plus 5 and then evaluate at minus 5.
Okay, thank you.
No problem. So here you have minus 9 over 9. Here you have 1, and here you have 2. Any questions about this part? Yes, Abdullah.
وإذا كان عندنا A13
Okay, then you will take, this is a good question. You will take a second derivative for the third term. And then we will also have a formula because you need to multiply by an appropriate scalar. So we will give you the formula, the general formula, which you can apply for repeated poles with multiplicity greater than 2.
Okay, clear.
So the highest order term, treat it as distinct and use a different formula for other terms. So the inverse Laplace transform of this guy is, because I have here A11 over s plus 2 squared, then we have multiplication by time, right? Because t, the Laplace transform of it was 1 over s squared, right? So if I go from here to the time domain, then we have, notice the following. This term that corresponds to the square will have a time component. So 2t e to the power of minus 2t. You'll have e to the power of minus 2t for this term because you're just multiplying, you don't have an exponent here. And then we will have minus 1e to the power of minus 5t. The inverse Laplace transform is also different for repeated poles because you have a ramp now. You have multiplicity in the denominator. This is something else that we need to look into. So what if we have more than 2 repeated poles? It's similar to the 2 poles case, and there are expressions for it. Look at expressions 77 and up through 79 handout 3. Let me pull it up real quick just for completion. Let me open the handout and show it to you. Do you see my handout?
Yes.
So you see here we have something similar to the highest order. Then the second order we have the derivative. Then once you take the second derivative and you keep going, you have to divide by, let's say for the second derivative you have to divide by 2 factorial. Here we divide the factorial for the a12 because you're dividing by 1 factorial, which is 1. The general formula is as follows. Yeah, and after the inverse Laplace transform, you will have something like this. There's a general formula somewhere in the handout, I believe. But even if it's not there, then what I want you to look at is that you have to divide by the factorial and you keep going. Okay. So the next item in the agenda is complex poles. So we have 2 poles, one at -1 plus 2j, and the other one is -1 minus 2j. So we can do it in multiple ways. So the first way is to do it, treat them as 2 distinct poles, and we will have a corresponding K1 and a corresponding K2. And then you will notice that K2 is simply the conjugate of K1. And then you will have exponent with complex numbers, which is technically true, but maybe not that desirable because we want something that is, let's say, we want a real valued function. This is not a real valued function. This is a complex valued function. It's still a function of time, but you have complex parameters in the expression. So we want real valued functions. So there is no issue with dealing with complex valued functions, but real valued functions are nice to deal with. You can also, I mean, if I go to the same example, let me go back just real quick. I can still convert this to a real valued function using Euler's identities. If I go back to something I showed you last week, maybe, we have these identities, so you can still manipulate the system and get some representations in terms of sine and cosine functions. But we will look at it also differently. We will have a different way alternative way of looking at it. So there are multiple ways to solve this actually. But this is just one way that we're looking into. And there's another way that we'll discuss next. Where is the slide? Yeah. So one thing to notice here is that this can be expressed as BS plus C over S plus A squared plus omega squared. So if I have complex poles, then I can represent them like this, right? Now, what is this? This is simply, so you have 2 terms here. So we can relate one of this. So we have BS. So this guy, we can relate it, this term, we can relate it to the cosine function. And this term we can relate it to the sine function with appropriate scaling. Okay, so first you need to represent this as in the following form. So for the B and the C, it's very clear that B is 4, C is 8. And then you do square completion in order to find A and omega. So S squared plus 2S plus 5 is equal to S squared plus 2S plus 1 plus 4, which is equal to S plus 1 squared plus 2 squared. Now, the first one is simply B multiplied by shifted cosine. Why? Because we have, so let's look at it separately. So I have B multiplied by S over S plus A squared plus omega squared, right? If I look at the Laplace transform table, we have something of the following form. We have a shifted cosine. We have a shift in the time domain. We have a shift in the frequency domain, which corresponds to a shift in the time domain, which corresponds to an exponent in the time domain. Because we do that, we can represent this as the following function. So you have a shift, time shift, because I have a shift in the frequency domain, corresponds to multiplication by exponent in the time domain. And then we have sine omega t. Now, similarly with the sine function, we have c over s plus a squared plus omega squared. Now, again, with simple algebra, you can get a certain parameter here, where then you have multiplication by an exponent, and then you have multiplication by sine of omega t. This is just to show you that we can still handle complex poles using the inverse Laplace, using the partial fraction expansion. And there are multiple ways to go around it. One way is to do it business as usual, treat them as distinct poles. The issue with that is that you will have a complex valued function, but you can still convert it to a real function using the Euler's identity. The other method is to use completion of squares. And with completion of squares, you can get, you'll be done. And both methods are equivalent. Okay, is it clear? Do you want me to go through it again? Actually, we also need some additional terms here for completion, so that if this is S plus A, so we can match it. And then because I add A here, so we have multiplication by B, we need minus AB. Okay, so we have a shift in the frequency domain, which corresponds to multiplication by exponent, and then we have this guy. C minus AB is a constant. You need an omega here, so you can multiply by omega and divide by omega. So you have C minus AB over omega, some coefficient, some constant, and then we still have an multiplication by exponent because we have a shift in the frequency domain, and we have sine omega t. Is it any questions? All right. Then the next order of business is to deal with if when it's not strictly proper. So if f is proper but not strictly proper, we can use long division to express it as k plus g, where k is a real number and g is a strictly proper function. For example, this function is equal to 1 plus something strictly proper. This other function, this 1 plus something strictly proper is simply 1 plus, again, you use partial fraction for this guy. You have 2 over s plus 1, and then you have minus 2 over s plus 2. So what is the inverse Laplace transform of 1? It's the impulse function. What is the inverse Laplace transform of t over s plus 1? It's 2e to the power of minus t. We have a shifted step. Similarly, you have 2e minus 2t for t greater than or equal to 0. So the question is, how do we get this 1? We use long division. Do you guys remember long division from Math 001? Anybody remembers long division? You don't remember long division? A little bit. Okay, we will revise it. So basically, you take the numerator, you put it over here. You take the denominator, you put it over here. Then you multiply by whatever you need to multiply in order to cancel the term. So if I multiply by 2, I have 2 squared plus 8s plus 8. Take a negative sign of everything. So we're left with minus 7 minus 5. So this is equal to what? I take this guy. So I have 2 plus minus 7s minus 5 over the same thing, s squared plus 4s plus 4. So we do the long division. You take the numerator, put it inside, and then you take the denominator, put it outside. You find some number to multiply by, so that we cancel the higher order terms, and then we can stop. So we have 2 plus these two, this guy. Then the inverse Laplace transform of this guy is the impulse function, and then you can do partial fraction for this term. We have another example here, but time does not allow us to go through it. So I will get back to this part next on Wednesday, inshallah. But this is the general idea that we want to go through. So basically, you have a differential equation that can be complex to solve. You do that Laplace transform to get an algebraic equation. Then you do the inverse. Then you have a fraction. Then once you have that fraction, you do inverse Laplace transform to get the solution to the differential equation. With that, I will stop, and then I will continue the discussion from here on Wednesday, inshallah. Given this space, I think we can finish the Laplace transform on Wednesday, and then that will conclude the material needed for test 2. Once we're done with the Laplace transform, we will move to the next unit. I'll take a minute for questions. And with that, we can dismiss the class. So if you don't have any questions, feel free to leave the session. Otherwise, I'll be here for a minute or two for your questions. For the remaining questions, for those who have questions or comments or things that they want to say.